All right, so I want to investigate the relationship between extension and force and essentially solve problems using Hooke's law, right? This is not a hard topic, it's very easy, right? Yeah, it's very easy topic. We should be able to complete it or complete most of it today. So when a force is exerted on a rubber cord, when you see a force being exerted on a rubber cord, um, it will deform, right? Essentially by stretching. So whenever we have a rubber cord, I say a string, and we apply a force on our string, we see that there is some form of deformation or it changes its shape, right? So this force is classified as an elastic force or a tensile force, right? Why? Elastic force meaning that when we pull it, it will apply a force to go back to its original shape. And tensile force meaning it acts along the length of length of the string, right, or the length of the wire or length of the spring. So the act of stretching, let me just bring up my mic, see if this helps a little better with the sound, right? So the act of stretching is a resultant of the attractive forces between the molecules, right? So whenever we stretch a spring, you find that the molecules will are the ones that exert that force to bring it back to its original position, right? All right, so objects that usually show this force are rubber cords, elastic bands, thin wires, and springs, right? And before we move any further, we'll bring up a short activity, right? So just give me half of a second to set up. So anytime we apply a force to a spring, we will see that the spring will put up some form of resistance or will try to go back to its original position, and we will discuss that further down, right? So I bring up the activity here. It won't be long, right? All right, so tell me if you are seeing this. Are you seeing this?
Yes,
Yes,
sir.
sir.
All right, beautiful. All right, so we have our spring here, right? Let me fix this. Right, so we have our spring here, and we have, let's put our displacement. So this is our original position of the spring, right? This is our original position of the spring, and we know, let's just say we apply a force. So if you observe, when we start to apply a force, you find that the handle here starts to hold on the spring, and you say it's at zero, the applied force is zero. Let me see if I can get my ruler. Yeah, all right, that's perfect, but our original position is zero. And say we move this to say 5 or 10 newtons. Let's move it to 10 newtons. So whenever we move or we apply a force, we realize that there's a change in the extension. So we see that there's a movement in the extension. The string moves from this position to 0.5 meters to the right based on our, our, our force. Now, if we double this, say we double this from 10 newtons, right? 10 newtons to 20 newtons, look what will happen to the extension. If we double, right? It's very important. If we double to 20, what is our extension now, right? What is our extension?
0.1.
0.1. So it was at 0.05 at first, 0.05. And if we double the applied force, what happens to our extension?
Doubles.
Right, it also doubles. All right, that's what we want to achieve first. Now, if we remove our force now, remove our force, we put it back at zero, and we let it go, you realize that it goes back to its original position. It doesn't change. It returns back to its original position, right? Doesn't change. So that brings us now to Hooke's law, right? We can move now into the law that governs this, right? So we were here, and let's move on now. So so as we said, when a force is exerted on a rubber cord, it will deform by stretching. So we saw where the string, the shape of the string was changing when we added a force, and the more force we added, we saw that the spring also deformed even more, right? So we can move now to the law that actually governs the spring. So this law governs the behavior of the spring under force. So Hooke's law is used to study the elasticity of materials, right? Any material that is elastic, any material at all, it could be a rubber band, it could be any form of material, a spring. Hooke's law governs this, right? Hooke's law studies this, and we know everything about it because of Hooke's law. So it states that provided that the stretching force does not um extend a spring beyond its elastic limit, right? I'm just get my pad here, my writing pad, and add this person. Right, and get my pen. All right, we're set now. So, provided that the stretching force does not extend beyond its elastic limit, and we'll get to this guy in a few minutes, right? In a few minutes, we will know what this guy means. The extension of a spring is directly proportional. Right, we saw this already, directly proportional. We know about this already, right? We'll recap it in a few seconds. So just bear with me. It's directly proportional to the stretching force. So the force that causes spring to stretch, right? The extension of the spring is directly proportional to that force. And we just saw that a while ago. So in other words, as the load of the spring doubles, the load being that force that caused the spring, the load is that force that causes spring to change. So if that load or the force, right, force F, if that force on the spring doubles, the extension on the spring will also double, right? And we just saw that, right? We just saw that. So we realized we just did it a while ago. We extended we extended the force from say 10 newtons to to, to 20 newtons, and we saw that the extension of the spring moved from 0.05 to 1, which means that it also doubled, right? So we proved this a while ago. So this law is obeyed until the limit of proportionality is reached. This is the same thing as this guy up here, right? Elastic limit, limit of proportionality, right? Somebody want to guess what this means before we actually go into it, right?
Sir, the limit to this spring can stretch.
Right. So that is you're correct. So the limit that the spring can stretch, but you miss out an important point. So there's a limit that spring can stretch without, and after it stretches beyond this limit, it is not able to go back to its original position. Right? You know that spring in a pen, right? When you were in grade 7, you used to take out the spring out of a pen and you used to stretch it, right?
Yes,
It
sir.
right, and it's not able to go back the way that you want it. So what you have to do,
Stretch out.
yeah, it eventually stretched out. So what you have to do, you had to either throw it away,
Try to close it back together.
Throw it away.
or you could stuff it with paper, right? I didn't have enough money to purchase another pen, so I had to stuff mine with paper, right? But it reached the limit of proportionality, which means that it's no longer useless. It's no longer able to do its function, right? It's no longer able to do its function, so we have to get rid of. So it's no longer it doesn't obey Hooke's law anymore. It doesn't obey Hooke's law anymore. All right. So we can move on. Are we good here? We understand Hooke's law, right?
Yes, sir.
All right, good. Uh, okay. Now the um so as we said, this law, let's just repeat, this law is obeyed until the limit of proportionality is reached when stretching a material. Um, so after the elastic limit, the law is no longer obeyed. We just established that. So the material now becomes permanently deformed. I wish I could get a picture quickly, right? The material becomes permanently deformed and no longer applicable to Hooke's law since it does not return to its original length. It doesn't go back to that length that it was when the force is removed. Boy, I wish I had a picture that could show you what we're talking about. Oh, well, we have one here, right? We have one here. So this is our original length. This is our original length of let's say this is 10 meters. Let's say this is 10 meters. Our spring here is not actually 10 meters, but let's just say for argument's sake, it's 10 meters. And we stretch this now to 0.22, sorry, it is now at say 15 meters. We stretch this to 15 meters. What if we let go? What will happen?
It will go back to its
Go
original
back to
form.
So
10.
it go back to 10. And now if we stretch that 15 meters down to 20, right? It hasn't reached its elastic meters yet, all right? So it's it's now at 20. It's now at 20. What will happen? It will go back, right? It go back to its original length.
Yes, sir.
Right, because it hasn't reached its elastic limit. But what if this is what the elastic limit look like, right? If we stretch it so far, so this is at 20, suppose we stretch it at say 40 or 50, we got something heavy and we placed on it, right? We will find that it will look something like this. So it will no longer look like it. So this was 10, this now looks like 14. This now look like 14 meters, right? 14. And there's no force attached to it. So our spring is now deformed. We'll have to get a brand new spring. We can't use this one anymore. I'll have to throw this away. Right? So are we good so far? You want me to go over it again or are we okay?
Sure, go over it again, sir. Come on, just join.
Sir, go over it one more time, please.
Who is that? Alert?
Yes, sir.
And why were you late to my class, sir?
Sir, my
It's
internet that
because
give problem, sir.
the other
And I have to
students
plug out and
wanted
plug
me
in
to
about.
go over it. That's why I'm going over it. Right? If it was you alone, I would make you watch a video over from the beginning. Right? So we have our spring here, right? Our spring is 10 meters, originally 10 meters, and we apply a force, right, in this direction. We apply a force in this direction, right, and it now stretches to 15 meters, right? What will happen if we let this go, right? If we let this go, what will happen?
Sir, you return back to 10 meters.
We return back to 10 meters, precisely so. And let's just say we haven't reached our limit as yet. So we stretch this even further down to 20 and we let it go again. What will happen?
Sir,
Go back.
return back, sir.
Right. So it would eventually go back. So it depends on the amount of force that we place on it that determines the extension of the spring. Now, say we stretch the string so far, say 40 meters. We stretch the spring all the way down here. Let's say this is 40 meters all the way down here. And we let it go and it looks something like this, right? This would show that it has reached its elastic limit, right? And it's no longer useful, or it's no longer obeys Hooke's law, right? It no longer obeys this law right here. All right. So are we good?
Yes, sir. Yes, sir.
All right. Uh, let's move on. All right. So we have a graph here. Now, going back to our Hooke's law. So we said that Hooke's law states that provided that the stretching force does not extend the spring, beyond its elastic limit, right, the extension of a spring is directly proportional to the stretching force. So this means the directly proportional means that if the force increases, right, the extension of the spring will decrease or increase. But what happened to the
Or
extension?
decrease.
No, it's directly proportional.
Repeat.
If the force on the spring increases, what will happen to the extension of the spring?
So it's gonna get longer.
It's going
Right,
to
so it's going
increase,
to
sir.
get longer or increase, right? So,
Sir, my internet now work so good enough, sir. So every minute it's up.
no problem. All right, not a problem. So we go back. We got a graph here, right? And this is our force or weight, right? Um, so it increases in this direction. This is also called force. Force is the same thing as weight, or weight is a type of force, right? And when it increases, what happens to the extension? Right? What happens to the extension?
So it doubles.
Right. So as I just said, um, if we go from say, well, it's kind of difficult to look at it that way, right? Let me see. Um, yeah, it's a little difficult to look at it that way, but essentially the same thing, right? So as we increase the, this is about 8. No, this is about 0.4, right? This is about 0.4, right? And this is about say 0. Let's say no, don't want to go too technical into the graph, but just to get an understanding, this is about 9, about 0.8 again. So this is 0.4, and we increase it to 0.8. So at 0.4, our extension is 2 centimeters, right? 2 centimeters.
Yes,
And
sir.
then when we increase it to 0.8, what happens?
It will go to 4.
It will go to 4, so it doubles. Right, right. So it doubles from 2 to 4, right? So when this doubles from 0 to 4 and it goes to 0 to 8, 0.8, this will increase from 2 to 4. Very easy stuff, right? Zero. What is happening up here? What is happening here? Why is this? What is this? Like, why does my graph look like this?
So maybe it reached its elasticity limit there, I
Right. So
guess.
it reaches its elastic limit. Right. Elastic limit. Right. So our elastic limit would be about an extension of 8, right? So 8 would be our elastic limit. So it has passed its elastic limit and now the spring is deformed, right? It will no longer return back to an extension of 0 if we remove the weight, right? So we are good so far?
Yes,
Yes,
sir.
sir.
All right, beautiful. Right, so now we have the moment that we have been all waiting for, right? Our formula. I've been waiting for this moment for a long time. So Hooke's law, as we said, is used to study the elasticity of materials. So the ratio is essentially the force over extension equal spring constant, right? You won't need to focus on this yet. Let's just work through the directional, right? The directly proportional. Let me see the time, right? So as you said,
Sir, could you repeat that, please?
yeah. So the ratio is force over extension, and this ratio is equal to our spring constant, right? So our spring constant is essentially unique to every spring, right? So every spring has a different spring constant. So it means how it's basically how strong our spring is, right? Basically, how strong our spring is, right? And we can look at that for a second before we move on. Can look at that again, right? All right, so we have our spring here. Are you seeing this?
Yes, sir.
All right, so we have our spring here and the applied force of 0, and let's just increase the force up from 0 to 20, right? 0 to 20, and our extension is 0.1. So make a note of that. Our extension is 0.1 at 24, a spring constant at 200 newtons per meter, right? 200 newtons per meter. Now, if we increase our spring constant, look what will happen, right? You see what will happen? If we increase our spring constant, we see that the extension is decreasing, but the force is the same. The force is the same. So, all right, look at it again. It was at 200. All right, so at 200 newtons per meter, our applied force is 20, right? Now we put it back at 0. Let's just put it back at 0 for a second. And we increase the spring constant to say 400. 400 Newton meters. So this means our spring is much stronger. It is thicker. It has more elastic force in it, right? More elastic force. So now we will apply the same amount of force at 20 newtons. 20 newtons. Now our extension is less. Why? Why is our extension less? Our extension was at 0.1 before, and it is at 0.05. Why is that so?
As a constant higher.
Sir, it have more elastic force, sir.
Right. So our spring has more elastic force. There's a larger spring constant. So therefore, our extension will be less. The more force that we apply, it's not going to be able to pull it as if there was a smaller spring constant, right? A smaller spring constant. So therefore, a smaller extension. Are we understanding? Are we good?
Yes, sir.
All right. Wonderful. I only heard one person.
Yes,
Yes,
sir.
sir.
All right, good. All right, so we can move on. All right, so as you said, the higher the spring constant, the stronger our spring is. So therefore, as I said, it is unique to every spring. Every spring has a different spring constant, right? And this comes down to our formula now. Our formula states that F is equal to K, which is our spring constant, times extension, which is in meters, right? Extension in meters, right? So if our force increase, so this is constant. Let's just say K is a constant. As you said, spring constant, and we're using one type of spring. And we say our force increases, right? Because they're in the same line, the force and the extension, they're in the same line. If the force increases, the extension will eventually what? Decrease or increase.
Sir, repeat.
If
Repeat.
all force is in the same line without extension, right? Right, they're in the same line. So force equal K times extension. So if we increase our force, what will happen to our extension again? Let's just repeating again or recapping. What happens to our extension?
Increase.
Increase.
Right, it will increase. Right, we just want to just make that clear before we move on. Right. All right, now. We are now at weight. Right. When we have, say, a spring, let's just say this is our spring, right? This is our spring, and we have a small weight on it, right? The force is up or down. Where's the force going?
Down.
Down.
Right, so the force is down. And we have another spring, but this one has a larger extension, so therefore there's a larger weight, right? The force is still down, right?
Yes, sir.
But it
Yes,
has a
sir.
larger force down. So this one has a larger weight than this one.
Group A.
Right. So force, as I said, is weight, right? Weight is force, the type of force, and they're both in newtons. We'll learn about this in the next class, hopefully. Right? Um, but we have a force equal mg. This is our formula to calculate the weight. So if we get a mass, say our mass is equal to 200 grams, right? How do we calculate our weight? So right back our formula, force equal. So how would we calculate our weight? How would we go about calculating our weight?
Sir, you divide the mass by force.
No, we want to calculate the force is the weight, right? Force is the same thing as weight right here.
Oh.
Yeah, force is the weight, right? Weight is a type of force. It acts downwards because of gravity. So acceleration due to gravity is 9.8, right? This, just remember that G, gravity, right? G and gravity. So we have our mass here. Now we want to calculate the weight that mass acts on the spring, or that weight, that force that the mass causes on the spring. So how do you go about calculating that? We have mass right here, right? Our mass is what?
200 grams.
Right.
Sir,
But
mass
Sir, we
times
multiply.
gravity.
Sir, you multiply mass by gravity.
yeah, so you basically multiply with mass times gravity. But before we go any further, we have to convert this to what?
Gram.
You have to move the grams to what?
Milligram.
Milligram.
No, you have to move grams to kilograms, right? Because any calculation that we're doing, any calculation that we're doing, we have to change the grams to kilograms in physics, all right? So let's convert this now. So 1,000 grams is equal to 1 kilogram, right? And we have 200 grams here, and we have x. So we cross multiply, right? Cross multiply. Right? So let's times them now. Let's cross multiply. So we have x times 1,000, 1,000x, right?
Yes, sir.
Yeah.
And 200. Yeah, we have our algebra coming. Thank you. So 200 times 1, we have 200. Right? So how do we get x now?
Divide 200 by 1.
Divide by
Right. So divide both sides by 1,000. And now we have, what is our final answer?
5, sir. 5 kilograms.
No.
0.2.
0.2 kilograms, right? 0.2 kilograms. So are we good
Yes.
so far?
Yes, sir.
All right. Any questions?
Oh, sir, me see it now, don't worry.
All right, so 0.2 kilograms times our gravity, right? What is gravity?
9.8.
9.8.
All right. So what is our final working out now? What do we get now? We have a
You
calculator.
must. I don't know.
0.96.
1.96.
How much you got?
1.96.
1.96.
Yes, sir.
All right. Yeah, 1.96. And our unit is in newtons, right?
Yes, sir.
Mm-hmm.
Newtons. So that would be N. So our force or our weight, remember force and weight is the same thing, is 1.96 in this case, right? 1.96. So are we good? Any questions?
No, sir.
All right. Thank you. All right, so we can move on. All right, let me just fix this quickly. This is off. All right, go ahead and share me. All right, so let's try this question together. So a car has a mass of 1.2 tons, right? So the suspension on the spring of the car, right? All the suspensions have a spring constant of 2.0 times 10 to the 5 newtons per meter. So when we add a mass of 1.2 tons, how far does the weight of the car compress its spring? Right? How far does the weight of the car compress its spring? So that's essentially the extension, right? All right. So remember our formula for Hooke's law. All right. Let's go back. Our formula for Hooke's law is
A times X.
I didn't hear that.
F equal kx.
Right. So F equal kx. F equal kx. Right. We have less than a minute, so let's just pause here and come back. Just use the same link, right, and join the class again. All right.
Yes, sir.
All right.